Ezra, so nice to meet you.
Nice to meet you, Pat. I'm excited to talk about the Hiden differential mass spectrometry technology today.
Really looking forward to it. Do you mind if we ask you some questions first?
Sure thing. Follow me this way to my office.
All right. Professor Clark, thank you so much for inviting us to your lab today. This all looks to be very much state-of-the-art. Perhaps you can walk us through the facility and outline some of the features of your research, equipment, and facilities.
Sure. So we are entirely a fundamental electrocatalysis laboratory. We look at reactions that span the entire range of more established reactions like water electrolysis and fuel cell technologies, all the way to more emerging reactions like CO2 reduction and hydrocarbon conversions. Our approach really spans a wide array of different perspectives, all the way from understanding surface reactivity and surface chemistry, all the way to reactor design and reaction engineering. And so really the cornerstone of our laboratory facilities are the analytical instruments that we use to quantify the product distributions that are contained in both the liquid streams and gas streams that emerge from these reactors.
So the instrument and application we are focusing on today is based around the Hiden Analytical HPR40 DEMS system. Can you explain more about what's going on there?
Yes, so the DEMS is an analytical instrument that can interface a mass spectrometer with an electrochemical reactor using a pervaporation membrane. And this configuration enables volatile electrochemical reaction products to be continuously sampled, identified, and quantified in real time. And this capability gives researchers the ability to continuously quantify their products, very rapidly screen new catalytic materials, and understand how their performance degrades or changes over prolonged utilization.
So this looks to be a compact and accessible system. Can you outline from a user's perspective the key attributes?
So the HPR40 DEMS system has an exceptionally high sensitivity to electrochemical reaction products, and also has a very good stability and mass resolution. So collectively, these enable exceptional performance for characterizing the products from an electrochemical reactor. Furthermore, the system is equipped with a software platform that enables not only the mass signals to be deconvoluted in real time, but also the electrochemistry and mass spectrometry data to be visualized simultaneously, which enables the user to understand on the fly what products are being made from their electrochemical reactor and how these signals scale with the reaction rates measured with the potentiostats, so that the two can be linked in real time and facilitate the user's high throughput screening of new catalytic materials or catalytic processes.
So I was also wondering what accessory you currently have connected to the sample inlet. Can you describe that for me?
So the HPR40 DEMS system has multiple different inlet options. Right now we are primarily using the electrochemical reactor interfacing inlet. And one of the really unique capabilities of the Hiden HPR40 system is that there are multiple different electrochemical reactors that Hiden offers that can be directly interfaced with the mass spectrometer. Each of these different electrochemical reactors has unique capabilities, unique reactor configuration and geometry, and it makes them particularly well suited for answering different research questions. So we have the type A cell, where the electrocatalyst of interest is separated from the pervaporation membrane by a thin layer of electrolyte. And this configuration is really the most simple reactor that they offer, and it is really well suited for studying catalyst materials that do not need to be continuously supplied with reactant species. So investigating things like electrochemical water splitting reactions. We then have the type B cell, where the electrocatalyst of interest is separated from the pervaporation membrane and actually isolated into separate chambers. And this configuration is compatible with electrolyte flow. And so this cell configuration is really well suited for quantifying the activity of catalysts that need to be continuously supplied with reactant. And one example of such a reaction is electrochemical CO2 reduction. Furthermore, great care was taken in the design of the type B cell to ensure that the cell exhibits optimal electrochemical characteristics, such as a parallel potential field between the working and counter electrodes. And finally, we've taken the type B cell one step further and modified it to make it compatible with performing electrocatalyst quantification by coating the electrocatalyst of interest directly on the pervaporation membrane. And this allows the highest sensitivity and the most rapid time response of any of the cell offerings.
So it'd be super to hear how these are performing in your current applications. Do you mind delving into that a little bit more?
We have used the type B cell to quantify electrocatalytic activity during potential sweeps for reactions such as electrochemical CO2 reduction over copper and silver electrodes. We've then used the modified type B cell to understand how the local reaction environment changes compared to the bulk reaction environment during these reactions. And finally, we've actually used this approach to understand and begin to elucidate the reaction mechanism. And so electrochemical CO2 reduction undergoes many different reaction steps, going from CO2 all the way to the hydrocarbon products that we produce. And so we've actually been able to use the modified type B cell to understand and directly observe the formation of transient reaction products. In our current applications, we are using the modified type B cell to very rapidly quantify the product distribution during continuous voltage sweeps at scan rates of up to 100 millivolts per second, which is an exceptionally fast quantification that is really unprecedented in this field. We're harnessing this capability to investigate catalysts for a wide variety of reactions, from hydrogen evolution, oxygen evolution, to more emerging technologies like CO2 reduction, CO reduction, acetylene semihydrogenation, methanol oxidation, and others. And so really we are utilizing this technology to not only understand how catalysts composition and structure influence catalytic activity and selectivity, but also how the application of dynamic polarization, how modifying the electrolyte composition influence these properties as well.
So can you tell me what other inlet options you plan on running with the system? Because it looks like to be a very versatile platform.
You're exactly right. The versatility of the Hiden HPR40 system was one of the main reasons that we ultimately decided to go with this instrument. Not only does Hiden offer the ability to directly interface the mass spectrometer with a variety of different electrochemical reactors, but they offer different inlet options that enable products to be sampled in entirely different ways. And two of these different inlet options that we will be using in the near future are the DEMS probe. This is a probe that is on the end of a flexible wand that can be directly inserted into any electrochemical reactor that is being used in the laboratory. It could be used in a typical rotating disc electrode reactor, a more conventional H-cell reactor, or anything in between. And this allows volatile electrochemical reaction products contained in the electrolyte to be continuously sampled, and so their accumulation can be monitored in real time. They also offer a capillary inlet option that enables gas streams to be sampled in real time. And this configuration can be used to sample the effluent of a all gas phase, zero gap electrochemical reactor operating at high current densities. And so in the near future, we will be using both of these inlet options and really harnessing the versatility of the HPR40 system to understand and characterize our catalysts and our processes in a wide variety of different electrochemical reactors.
So with that in mind, can you tell us how you see your future plans evolving and what part the QMS can play in these plans?
So the QMS is going to play a central role in our future plans. And really, the reason for this is that the QMS enables two things to be done that cannot be done otherwise. One is to quantify the product distribution and the selectivity of our catalyst in real time from second to second. And so this enables us to use this technology to actually understand how dynamic perturbations to the driving force of the reaction influence the catalytic performance of the material. And so one of the emerging areas that we plan to utilize the HPR40 system to investigate is the impact of dynamic polarization on the catalytic activity and selectivity. And so here what we're doing is we're actually changing the driving force of the reaction on the time scale that the system is capable of quantifying the product distribution. The other area where the QMS really opens up new avenues of research is investigating isotopic transient measurements. And so these measurements are performed by applying a fixed voltage to your catalyst and very rapidly changing the isotopic composition of the reacting species in real time and monitoring the resulting isotopic transient in the product distribution. And these measurements ultimately enable you to characterize and quantify the steady state coverage of reaction intermediates on your catalyst surface and their surface lifetimes. And in so doing, actually understand the origins of electrocatalytic phenomenon. So when you make a change to the system that ultimately results in a change to the activity or selectivity of the catalyst, what is the intrinsic origin of that change? We can get at that sort of information using these isotopic transient measurements.
Dr. Clark, thanks so much for the interview. Do you mind if we take a look at your lab?
Sure, right. Follow me right this way. Abby's doing an experiment right now.
Oh, awesome.
Hi guys, come on in. So this is the modified B reactor from Hiden. Our group has modified it a bit further just to create a lip on the working electro chamber. That way the compartment can actually fix onto the pedestal itself. And we also created a port for an electrical connection via a pogo pin. Since this modified B reactor is based off of the DEMS classic cell design, the catalyst is deposited directly onto the evaporation membrane. The evaporation membrane it then interfaces the mass spectrometer. To make assembly of the reactor a bit easier, I sputter coat a large sheet of PTFE with whatever catalyst of interest, and then I punch 14 millimeter electrodes so that way they're prepared ahead of time, so it just makes assembly a bit easier. And I'm just going to take one of those electrodes and I'm going to try to center it onto the pedestal. The pedestal is what actually fixes or mounts the reactor onto the sample inlet. And the pedestal contains a stainless steel frit that mechanically supports the thin film. And then I'm going to take my working electrode chamber and I'm going to ensure that the pogo pin is in contact with the electrode, and I'm going to align the bolt holes and press down in order to fix the working electrode chamber onto the pedestal. We use ion exchange membranes to separate the working chamber and the counter chamber of the reactor. These ion exchange membranes are also pre-cut in a 10 millimeter diameter. So again, I'm going to line that up. And then I'm going to align the counter chamber, again with the bolt holes, and I want to make sure that my inlet ports and my outlet ports are aligned as well. I'm going to press down. I'm just going to screw those bolts in. And there is the modified B reactor assembly. So now that the reactor and the lugging capillary are assembled, we are now going to mount the reactor onto the electrochemical sample inlet for the HPR40 DEMS instrument. I'm going to remove the cap from the inlet and I'm going to take an air gun to the O-ring that interfaces the pedestal and the sample inlet, just to ensure there are no dust particles or anything like that on the O-ring. I'm going to align the O-ring onto the pedestal, and I'm going to line up the reactor as best I can onto the sample inlet. I'm going to take my clamp and fasten the reactor onto the sample inlet very carefully. Just like that. So now the reactor is fixed onto the sample inlet. I'm going to take my electrolyte tubing and I'm going to screw my tubing into my reactor. I have 4 tubes, an inlet and an outlet for my working chamber, and an inlet and an outlet for my counter chamber. The working electrode chamber consists of 4 ports, 2 for the inlet and outlet, 1 for the electrical connection via the pogo pin, and the other port for the lugging capillary assembly. I'm going to ensure that these are nice and tight, so that way I have no oxygen leakage into my reactor. Once I connect my lugging capillary, I'm going to open that valve. I'm going to push some electrolyte into my reactor, and then I'm going to close my valve so that way the electrolyte is not depleted from my lugging capillary. And I'm going to make my electrical connections. So my white clip goes onto my reference electrode, my red clip goes onto my working electrode, and the blue clip goes onto the counter electrode. And now the reactor is mounted onto the sample inlet, and we can start our electrochemistry. So after the sample inlet are two valves. There is a needle valve and a solenoid valve. And the needle valve open and closes the passage of volatile species into the mass spectrometer. And the solenoid valve detects if any liquid actually enters the mass spectrometer. So it's sort of a safety valve for precautionary purposes. And therefore, if that valve detects liquid, it will shut immediately. So in order to start sampling products, you want to open the solenoid valve. And you open the solenoid valve by the sample inlet controller on the front panel of the instrument. And you're going to see that you're in standby mode. The light on the standby button will be lit yellow. And you'll see that your standby pressure should be anywhere in the -8 scale. Once you're ready to start sampling, you're going to press the inlet prevac button, and you're going to wait for the solenoid valve to open by hearing a click. And then the light is going to illuminate for sample, meaning that we're ready to open the needle valve. And the needle valve is going to be opened very slowly. We're going to open the needle valve while monitoring the pressure to make sure that we're not overloading the system. And once I observe the pressure in the low -6 scale, we are going to open the needle valve all the way, and we are now able to sample volatile products. Operating pressure in the mass spectrometer should be anywhere from 1 to 1.5 times 10 to the -6 torr, and standby pressure should be anywhere in the -8 scale. So considering I have two chambers, I have an electrolyte for my working chamber and I have an electrolyte for my counter chamber. So the first experiment that we're going to look at is just simple CVs over a platinum electrode in 0.5 molar sulfuric acid. On the right-hand side of the screen, we have our EC lab data or our electrochemistry data. So right now we are doing a potentiodynamic measurement known as cyclic voltammetry or CVs. And CVs is a powerful technique in electrochemistry that allows us to observe the electrochemical processes that are going on over our catalyst of interest at a fixed scan rate. So during a CV, you can set your potential range to a fixed vertex. And for my cathodic vertex, we can see the onset of hydrogen evolution reaction, or HER. And then for my anodic vertex, we can see the onset of oxygen evolution, or OER. And now we can see these products actually being formed while we monitor the mass ion currents of interest in the mass spectrometer with the MassSoft data, the MassSoft software. So in the MassSoft software, these are MID scans that allow you to monitor multiple mass ion currents of interest during one experiment. And this is also the electrochemistry is also at a fixed scan rate of 50 millivolts per second. And you can see the time response of the mass spectrometer is almost instantaneous. So therefore, if we take a look at this M/Z2 signal, you can see that in the electrochemistry, we have the onset of HER, and you can see the hydrogen production in the mass spectrometer. The time response of the mass spectrometer is almost instantaneous to the electrochemistry. But essentially, we are scanning the potential linearly at a fixed scan rate in order to see the Faraday processes that are going on over our catalyst. In our electrochemistry, you see that we have the current as a function of potential. So our current response is indicative of these Faradaic processes that are occurring over our catalyst. And again, this current response is indicative of a Faradaic process occurring over our electrocatalyst, and we can monitor these products that are being produced with the correct mass ion currents of interest. So now we're going to do CVs in 0.5 molar sulfuric acid with added 0.5 molar methanol to the solution. And we're going to monitor the 44 response, which is representative of the production of CO2. And you can see as the potential is scanned, there are 3 regions of this CV where CO2 is actually being produced. And we can monitor that in real time with the mass spectrometer. Methanol oxidation is known to have other products at these potentials, but we are monitoring 44 because that is the dominant product of methanol oxidation over a platinum surface. So you can see as we start the scan and we start to scan forward in the anodic region, we see that we have this anomaly known as the low potential methanol oxidation wave, and you can see the production of carbon dioxide in the mass spectrometer almost simultaneously. And then we get to this low region, and then we get to a higher region known as the, and more anodic region known as the high potential methanol oxidation wave, where carbon dioxide is being formed again, and then we see the onset of OER. And now we're going to scan in the reverse direction, or cathodically, and we're going to see platinum reduction, and then a reverse scan methanol oxidation wave. Because methanol oxidation occurs at these potentials regardless of the direction of scan. But you can see that the forward scan gives a much higher current response than the reverse scan. So this is just a view. In the mass spectrometer, there are multiple views in order to observe your transient data. And so far, we've been looking at the graph views of these MID signals, of these MID scans. You can also pull up an Excel file of your data that essentially shows your data acquisition rate. And here you can see that we have a data acquisition rate at about 3 data points per second. This data acquisition rate can be adjusted through a variety of variables in the mass spectrometer, including emission current, and dwell and settle time, and adjusting the multiplier. Data acquisition is going to vary based on the gain range that you're in and the abundance of the species that are actually entering the mass spectrometer. But again, these variables can be adjusted to fit your particular interests. So again, this is just to show that these are 4 different MID scans in one experiment, so you can monitor multiple mass ion currents of interest as you're doing potentiodynamic or fixed potential or current experiments. And you can monitor these signals in one graph, or if they are, a lot of the times you'll have mass ion currents that give very different intensities and very different signal intensities. Therefore, it's easier to observe the graphs one by one. So you can pull up each graph separately. You can observe the production or consumption of the species of interest. So for our third experiment, we are going to do a chronoamperometry experiment, or a CA, where we hold the potential at a fixed voltage of interest while monitoring the current response. And then in the mass spectrometer, we are going to do a bar scan. And a bar scan fixes the mass ion current signal range, and then the instrument will scan each mass ion current value. Therefore, we can observe what mass ion currents are actually giving signal at that applied voltage. And the bar scans are useful when you don't know what is being produced over your working electrode. So for the MID scans, I used the SEM, or the secondary electron multiplier detector, and for the bar, the Faraday cup.